Yay! Our favorite type of series, things that never end. The math, the pain in math never ends. So on Tuesday we were talking about this problem. Let me remind you of the context. We have this function f, which we are going to be able to semi-easily find a power series for because it's a modified geometric series. And so we're going to use that modified geometric series to find a power series for this natural log function. Before we get into the series part of it, we need to figure out how do we get to g from f. So we're trying to build a little roadmap. What do we do to f to get to g? And so what we saw was when we integrate f, we end up with this. And that looks almost like g. So we look up at g, and if we take this expression here and multiply it by 2, it will be g plus a constant. Right, if we multiply this by 2, we will get g plus 2 times c is still a constant. So if we multiply this expression by 2, we're going to get g plus a constant. So we multiply by 2. Well, this integral already has a constant that's going to come out in the wash, right? The integral of f will end up, we always have a plus c at the end of that. So we can ignore this constant because it can get wrapped up into the constant that's going to emerge from this integral here, right? So if you multiply this by 2, we get g plus 2c. 2c is just a constant. And so then we come down here and we're like, okay, g plus 2c. But then we see that, oh, wait, this is going to have a constant that's going to come out anyway. So we don't really need to put the plus 2c here, because that's already going to have a constant in it that we can resolve. No need to have 2, because we'll just merge them together into one constant. All right, so that is what we're going to do to f to get to g. That's our roadmap. It tells us how to build g from f. So let's go ahead and build f first. So we know the geometric series right there. And we need to build this from that and then possibly modify the interval of convergence if necessary. So the first thing I notice is that we need to have a plus in the bottom instead of a minus. And then we need to have an x squared instead of an x. So what we can do first is replace all the x's with negative x squared. So I'm going to come up here and replace the x's with negative x squared. So it's still going to start at 0. And we're going to replace the x with negative x squared. And we'll deal with the interval of convergence also. So if we look at that interval of convergence, it's negative 1 is less than x is less than 1. So we also replace this with negative x squared. And see if it changes. So that'll be our interval of convergence there. So let's simplify this. So when we come in to simplify this, we end up with a switch, negative 1 to the k, and then we end up with x to the 2k. And over here, we can multiply everything by negative 1, so that's going to flip the inequalities. So it's going to look like that. But then we don't like the inequalities to be backwards. We like to think left to right. So we can just rewrite this as negative 1 is less than x squared is less than 1. And then we're in that situation where we've talked about doing this algebraically or graphically. When you look at this, the left side of this compound inequality is always true. Right? X squared is never, it's always greater than negative 1. And so you can say, oh, well, the solutions to that inequality are the same as the solutions to this inequality. And then you can take the positive square root of both sides. And the positive square root is going to be absolute value of x over here. And lo and behold, we get back to the exact same interval of convergence. So it didn't actually change the interval of convergence. So that's the algebraic way to do it. You could also do it graphically. So we're almost there. We're not there quite yet. What's the other thing that we need to do to get to this? So we replace the x with negative x squared. What else do we have to do? Multiply by x. So now we're going to multiply by x, and that's going to give us f. So this is going to tell us that f of x is equal to x multiplied by this power series. We've seen that we can just pull it inside. So we're going to have negative 1 to the k, x to the 2k plus 1 when we multiply by x. And we've also seen that when we multiply by x, we don't change the interval of convergence. And that's sort of based on the ratio test. And the ratio test is a sub k and an a sub k plus 1. And if you multiply them both by x, the x cancels, so it doesn't change the interval of convergence. So now we can go over here and try to build the power series for g. So g is 2 times the integral of f. Well, f is this power series that we just created. And we'll worry about the interval of convergence in a moment. What we saw on Tuesday was that if you integrate or differentiate a power series, the endpoints don't change for the new interval of convergence, but maybe convergence or divergence at the endpoints could flip. Something could flip. So now we have an expression for g. So let's go ahead and do this integration. So when you integrate a power series or differentiate a power series, you're just dealing with a glorified polynomial. So we do what we normally do with a polynomial. When we integrate, we add 1 to the exponent, divide by the new exponent. Negative 1 to the k, that's just a constant. Constants always just float when you differentiate or integrate. So we're going to add 1 to this exponent. And we're going to divide by the new exponent. And when you do an integration, you're going to end up with a plus c also. So we could put a plus c out here. And so that's that c that is also absorbing the c from up there. And let's check our index here. If we were to look up here, if we just come off on the side to say, hey, let's make sure we index this properly. This starts at 0. So inside here, the very first term when you plug in 0 is x. The next term, if you plug in 1, you'll get a negative 1 here, and you'll get an x cubed, and it's going to go on like that. And so we are integrating, so we want to just make sure that our index matches what we would get if we integrated this. So if we integrated that, isn't the first term there going to be x to the 2 over 2 if we integrate? So we just want to make sure that that's what we get down here. And do we need to modify this, or can we still just start at 0? Will we get x to the 2 over 2? Yeah, if we plug in k equals 0, we get x to the 2 over 2. So that's going to work. So the index doesn't have to be shifted. We saw when we differentiate, we have to jack that index up and start at 1 instead of 0 if you differentiate, because you're losing terms. But when you're integrating, you're gaining a term, it doesn't matter. The index is going to stay the same. So there is our power series for g. Couple things left. Let's first resolve this constant. So when we look at g, what is g of 0 if we look at the function? 0, right? If we plug in a 0 over here, we get natural log of 1 plus 0, which is natural log of 1, which is 0. So let's resolve this constant. So we know that g of 0 must be 0. So now we want to think about plugging in 0 here for x. And what happens to all of this when we plug in 0 for x? What happens to this? It's all 0, right? Like the very first, one thing we have to make sure of is that there's no constant in here. If we plug in 0 for x, does every term have an x? And the answer is yeah. Because when the k is 0, our very first term here is an x squared. So this is a glorified polynomial. All the terms have an x in them. And so when you plug in 0, this whole thing goes to 0. So we have that. And what does that tell us c has to be? 0, right? We have this equation right here. C plus 0 is 0, so c's got to be 0. So therefore, our conclusion is that g of x is 2 times this integral, this summation starting at 0. This is our power series now. We've resolved that weird constant that's hanging out on the end, and that often happens that it's going to be 0. So now the only thing left, we have that our interval of convergence, we know the goalposts, we know the left endpoint and the right endpoint. We just have to double check whether there's convergence or divergence at those endpoints. So we test the -1. So let's test x equals -1. And we're going to test x equals +1 and see if we have convergence or divergence. So we've seen a million times that this constant out in front doesn't matter. So when we're analyzing convergence of the series part here, we can forget about that. That doesn't matter. Nor does it matter whether we start at 0 or 5 or a million, so we don't even have to put that piece in. So if we plug in -1 here, -1 to the 2k plus 2. -1 to the 2k plus 2, what is that equal to? Say again?
1.
Yeah, 1. Does everybody agree? Is this index, think about this index here.
Because it'll never not be even.
2k is always even, right? No matter what you plug in for k, you plug in an odd or an even, and you multiply by 2, you end up with an even. And if you add 2 to an even, you have an even. So this is always going to be -1 to an even, so this can be reduced to just 1. Now we have this alternating series. And we don't have to get into the weeds. It's an alternating series, so we could say, step 1, step 2. But we want to think just sort of more streamlined when we're dealing with endpoints. We don't want to spend too much time on the endpoints. What kind of is this alternating series going to converge?
Yeah.
Yeah, because we have our two basic facts. The limit is 0. At the limit of the a sub k, remember that a sub k is this part for an alternating series. And that definitely is going to 0. And it's decreasing. And it's decreasing because the only k's are in the bottom. And so if the bottom's increasing, the fractions are decreasing. So this is going to decrease to 0. An alternating series with a sub k decreasing to 0 converges. So this converges by alternating series test. But we don't have to write out the details when we're dealing with an endpoint. All right. Now let's plug in the 1. And the 1, when we plug it in, is not going to look much different. What is that numerator when we plug in a 1?
1.
1. So we get the same thing. This is also going to converge by AST. Because the a sub k, once again, is decreasing to 0. That's the essence of the alternating series test. A sub k, which doesn't include the switch, decreases to 0. So therefore, we can wrap up. This is our interval of convergence. What we're seeing is that we are gaining convergence at the endpoints. And this is a very common pattern that when you integrate, you may gain convergence. When you differentiate, you can lose convergence. Very common. So that is going to be the hardest question on the test, doing this. Figuring out your, this is key, figuring out your template. How do you get to G from F? Do you integrate F? Do you differentiate F? And then you have to modify the interval of convergence. So that is the tricky part. So let's take a look at these two general examples. It's very common if the center of a power series is 0, it's very common that we can, if they ask us for a power series centered at 0, it's very common that we can just modify one of the known power series. So those known power series are the next two slides, those 12 power series. So this is considered a known power series. So to find a power series for this function f here, it's not too crazy. What are we going to do to get the power series for f? Do you see what we could possibly do? Is there a way to get rid of that square root so that we sort of have a very similar look here? Obviously, this x here gets replaced with an x squared at some point. But this has a square root, this doesn't. Can we do something with that square root to...
Can you factor out a 1/2?
Yes. Yeah, right? The superpower for log, you can pull the power down as a coefficient. Right? So this could be turned into 1/2 natural log of the quantity 1 minus x squared. So that says, okay, let's take this power series. What we're going to do is multiply it by, what are we going to do up here? We're multiplying it by, what's going to be the coefficient then here?
-2.
So if we focus on this right here, we have 1/2 times that. So it's going to end up being a negative 1/2 natural log of 1 minus x squared is going to be okay. What are we going to do in here then? What's the difference? So we added the 1/2, or multiplied by the 1/2 out in front, and then we replaced x with x squared. So if we replace this x with x squared, we get x to the 2k. That's still going to start at 1. So first we have this, pull down the 1/2. The 1/2 is a multiplier. The natural log part of it is coming from here, but we have to replace the x with x squared. And if we replace the x with x squared in there, we have to replace it in there. So that's going to be our power series for function f. And then we have to modify our IOC. So our IOC was this when it was just x. What are we going to put in the middle there?
X squared.
X squared. This multiplication of a constant does not change IOC. If you multiply by a constant or a power of x, that's not going to change the interval of convergence. But when you do a replacement, it does. And so we have to put the x squared in here. Once again, if we do this algebraically, it's always greater than -1. So the only part of the inequality that matters is that. And then we're going to do our clever little square root of both sides. This inequality, before I take the square root, everything's positive. X squared, or at least not negative. Right? Nothing's negative, so we can take the square root of both sides. And when we take the square root of both sides, we're going to get absolute x less than 1. And so that tells us that our IOC is going to be -1 to 1, but we are not going to include any endpoint. So we lost convergence at that left endpoint. That's our new IOC. Let's try one more of those. So we have a known power series for arctan. Looks a lot like sine. The only difference is that for sine, we have factorials in the denominator. So how are we going to get the power series for f? What are we going to do to this x so that it matches? We're going to replace this x with
4x squared.
4x squared. Okay. We have a power series here that's based on x. We want one that's based on 4x squared, so we just replace that x with 4x squared. And if we replace that x with 4x squared in the expansion, we come to the inside, and that's the x there that has to get replaced with 4x squared. So we're going to come inside. We have our constant right there, -1 to the k is constant. There's no x in it. And then we're replacing this x with 4x squared. So 4x squared to the 2k plus 1 divided by 2k plus 1. Well, then we have to go to our IOC and replace that. So we have the original IOC includes both endpoints, negative 1 and 1. And we're replacing with 4x squared in the middle. So that's going to be our modified interval of convergence. Come over here. Let's do a little simplification inside this. So the 4, let's take this exponent and distribute it across. So we're going to have a constant of 4 raised to the 2k plus 1. And then we'll have our x part here. We're going to have x to the 4k plus 2 divided by 2k plus 1. And whether you put this 2k plus 1 under the x part of it or under this, it really doesn't matter. Now that I've written it out, it probably makes more sense to actually put it under the other thing that has no x's. It does not matter. But let's just do it this way so that the x's come last. That's at least how we should be thinking of a power series. It's constants multiplied by powers of x. We often will write this constant under it. Doesn't matter. So there's our power series.
Okay, so like the goal was to just get rid of the dude in front of the x. Like you don't want a coefficient.
Yes, we would like this to just be a power of x, not a power of a constant times x. So we want to sort of peel out that constant part and leave, bless you, just the powers of x. And then this we can simplify over here. First, we're going to multiply by 1/4 all the way through. We multiply by 1/4, we get that. And then we have our algebraic trick. Oh, x squared is never negative, so it's always bigger than negative 1/4. So the solutions to the original compound inequality right there are the same as the solutions to that non-compound inequality where everything's positive, which means you can take square roots. If you have an inequality that is true and it's all positive, then you can just take a square root. So that's going to give us absolute x is less than or equal to 1/2. And that will tell us that our IOC is going to include endpoints negative 1/2 to 1/2. That'll be our new interval of convergence.
And why don't we have to test the endpoints?
So it's a theorem that tells us if we integrate or differentiate, and we're not going to prove that theorem. In advanced calc, you would prove that theorem. The rule or the theorem says if you differentiate or integrate, the endpoints can't change, but convergence or divergence at the endpoints could change. But the endpoints themselves aren't going to change. So you still know the left and right endpoint. Those won't change. So that part's just a theorem that we're not going to prove. But it's a fact that makes our life a lot simpler. Because if you differentiate or integrate, you only have to test the endpoints. You don't have to You could, now if you wanted to, you could take this whole series and just apply the ratio test. You can do that. And you will get this interval. You could just do the ratio test here, and you will get this interval. It's just that if you're integrating or differentiating, the shortcut is that the endpoints aren't actually going to change. Convergence at the endpoints is not going to change. What am I trying to say? If you differentiate or integrate, you can only gain or lose convergence at endpoints. You're not going to expand the interval or shrink the interval. So this shrinking of the interval is not because we differentiated or integrated. We just did a substitution. So let me reiterate. If you differentiate or integrate, you don't change endpoints. You just have to retest the endpoints. If you do a substitution, you don't even have to test the endpoints. Right? We're not even testing endpoints here. If you do a substitution, you do the substitution into the series and into the interval of convergence, and you end up with your new interval of convergence. We didn't even have to do any testing at all here. Substituting is even easier than differentiating or integrating because you don't even have to test endpoints. But if you differentiate or integrate, test endpoints. So then we have our 12 series here. So for the exam, I'm going to ask you to know 5 of them. I'll tell you on Tuesday which 5 I want you to know. It will always include the geometric series, though, because the 6 on this slide are all based on the geometric series. And then this next one is just an integral of the geometric series. This one's called the alternating geometric series. I explain how you get to it. You just replace this x with negative x all the way through. This is the integral of the alternating geometric. Just integrate term by term. So here we just... Now this one I integrated and I did re-index it. So if you're integrating, you would get x to the k plus 1 over k plus 1. But then I re-indexed it so it starts at 1 instead of 0, which is why this is not x to the k plus 1. So you can play with that and just sort of see how that's done. And then this is the next most important one. So this one, we are going to integrate that log 1 above. So number 4, if we integrate that one, and then do a replacement. This one, arctan. This one's very cool to get to. If you look up here, what is the derivative of arctangent? The derivative of arctan.
X over x squared plus 1.
Very close. Not x over, what's the numerator?
2x.
1. Right. For arctan, the derivative is 1 over 1 plus x squared. Right. No x's up top, just down below. 1 over 1 plus x squared is the derivative of arctan. That's almost this. If you replace this x with x squared, you do have the derivative of arctan. So how would you get to arctan from the derivative of arctan? Integrate. So if we replace this x with x squared and then integrate, so replace x with x squared and then integrate, we get this. And the interesting thing is that one, when we go look at our second half dozen series that are based on e to the x, which we talked about a little earlier, which is why there's some highlights on here. So e to the x is that one. I can probably erase those highlights now because we can't even remember what those were about. So there's the e to the x, and what we notice is that the odd powers of e to the x form the sine power series, except we also throw in a switch. The even powers form the cosine power series, but we also throw in a switch. That looks almost identical to arctan. The only thing that's different from that in arctan is the factorial. It's the only thing that's different. If we go back and look at the arctan one, right? It's all the odd powers with the switch, but there's no factorials in the denominator, so it looks identical to sine, except for that factorial. So sine and cosine, though, come from e to the x. Sinh and cosh look almost identical to sine and cosine, except everything is positive, and these are exactly from e to the x, which we saw back when we did hyperbolics, and we saw that cosh of x is e to the x minus e to the negative x divided by 2. That equation will hold if you look at them in terms of power series. And then this is the new one. So this is going to be the hard one. We're going to do it today. This is called the binomial series. But what I want you to focus on is that this is just the geometric series with binomial coefficients. So we have to figure out the binomial coefficients. We've talked a little bit about factorials, and we'll talk about that today. Now, the binomial series is a weird one because all of the series that we've done so far, you can find the interval of convergence. You can't find these yet. These you can't do until advanced calculus. So the intervals, the IOCs for the binomial series will always be given to you because those series have such weird patterns that we can't use the ratio test for them. All right, so here's where we're at. On Tuesday, we were doing Taylor polynomials. Today, we are doing Taylor series. There's no difference other than that. That's it. Just the dots. Taylor polynomial stops. P sub 3 goes up to x cubed. Right, and stops. Taylor series, we just keep going forever. But we use the same pattern that we did with our Taylor polynomials. We use the same pattern to find all of these coefficients. All right, so Taylor series is just a Taylor polynomial with plus ... at the end. This guy, Maclaurin, took Taylor series and said, hey, if you center it at 0, let's name it after me. And so if it's centered at 0, it's called the Maclaurin series. It's just a Taylor series centered at 0. It's nothing super special. Okay, so for this Taylor series, this infinite series, this never-ending polynomial, this glorified polynomial, two things are important. We need to know what the x's are that causes it to converge, which is what we've been doing for the last week and a half. That's finding the IOC. Right? We want to know what x's cause convergence, what x's cause divergence. And we saw that the convergent x's are all grouped together in an interval called the IOC. The other thing that is subtle that we're not really going to get into is this idea that for what values of x does the Taylor series equal the original function? So this is a little abstract. The idea is that we're taking a function, sine, cosine, 1 over 1 minus x, whatever. We pick a function that you can infinitely differentiate. You can take derivatives forever. There's no division by 0. So you have a function that's infinitely differentiable. And the question is, building this, you can build it for any function that's infinitely differentiable. It doesn't guarantee that what you've built equals what you started with. So you're starting with this function, you're taking these derivatives, and we have seen through graphing that Taylor polynomial is getting more and more accurate. And in the long run, it's going to be true that if you build this Taylor series, it will actually equal the function that you used to build it from. But there is a little bit of a gap there to prove that the Taylor series is actually equal to the function that you used to create it. So that's done in an advanced calc class, that these two are actually equal. And it turns out that they are. That if you start with sine of x and you build this infinite series, that Taylor series will be the power series for sine. So Taylor series is a special power series. It's a power series that was created from a function. Right, so Taylor series, we start with sine or cosine or e to the x or 1 over 1 plus x, whatever. And we build the Taylor series by taking all the derivatives. So that is an example of a power series. But not all power series are created by starting with a function that you infinitely differentiate and form this thing. So there's a slight difference. But it turns out that if you have a function that has a power series representation, it will be the Taylor series. There's no other series for a function. If you've got a power series that represents a function, one and only one, they have to be the same. Whether you created it through all the derivatives or you found it in some other way, integration, differentiation, whatever. So it turns out that they will be equivalent. But there is a subtle gap there. When is the function equal to its Taylor series? So let's do one of these. So we have this function down here, and we're going to choose a center of 1. We're going to find the first 4 non-zero terms. We're going to write it in summation notation. And we may or may not do part C, find the IOC. So this is going to be an important thing to keep in mind. When you're given the instructions to build a Taylor series, if the center is not 0, you have no choice. You just need to pull out the tools and start taking derivatives. You got to build it. If we were asked to create a Taylor series or a power series that's centered at the origin, if it's centered at the origin, often we can take one of those 12 series that I just had up on the board and modify them like what we've been doing. Shift it, replace, multiply by a power of x. Like, there's things that you can do when it's centered at 0. When it's not centered at 0, 99% of the time, you're just pulling out the tools and start differentiating and do that whole table thing that we did for Taylor polynomials. So we see here, oh, center is 0. Don't even think about trying to use an existing series. If the center is not 0, start differentiating. And so this one said go down to 4. So first 4 non-zero terms. Not necessarily p sub 4. First off, if there's no coefficients that are 0, if we want 4 non-zero terms, would that be p sub 3 or p sub 4 if there were no non-zero term, if there was no 0 terms? If we want 4 terms, is that p sub 3 or p sub 4? P sub 3, because we have a constant and then an x and then an x squared and then an x cubed. So p sub 3, there's no 0 coefficients, is going to be 4 terms. But if you have 0 terms, maybe you're going out even further in terms of the power. So we want 4 non-zero terms, which doesn't necessarily mean p sub 3. So let's start with our function, y equals x to the negative 2. And we're going to differentiate. And so again, if you did so much of dealing with these Taylor series and Taylor polynomials is bookkeeping. It's just trying to keep everything in order and not get tangled up. So using this table process works super well. Now when we look at that and we recognize, oh, the center is not 0, so none of those are 0, so the first 4 non-zero terms actually will be p sub 3 in this case. So now we're going to pop the center in. So we're going to have y of 1, that'll be 1. Y prime of 1 will be negative 2. Y double prime of 1 is 6. And y triple prime of 1 is negative 24. Now again, notice that this did ask us for Taylor series, not Taylor polynomial. So we just ought to make sure that when we write this Taylor series, this is an entire polynomial, it's never ending. And so we're not going to call it p sub 3. The terms that we are going to draw on the board are p sub 3, but we have to put the plus dot dot dot. So we're going to call it something different. We'll call it t for Taylor series or p for polynomial, whatever. We've been calling things p sub 2, p sub 3. Let's just call this p of x. Some books will call it t of x. Doesn't matter. So 1 minus 2 multiplied by?
X minus 1.
X minus 1. The center is 1, so every term other than the leading constant will have an x minus 1 in parentheses. And this one is just raised to the first power. So what we have on the board right there is the tangent line to 1 over x squared at 1. All right, keep going. Next term is going to be plus 6. We're going to have an x minus 1 to the 2, and we have to divide this by 2 factorial, or you could just put 2, does not matter. And then our last term, negative 24 divided by 3 factorial, x minus 1 to the 3, and then plus dot dot dot. That's what tells me you understand it's a series and not a polynomial. Not a Taylor polynomial. So make sure you put the plus dot 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 if you're asked for a Taylor series. All right. Now this question asks for the interval of convergence. If you have the expanded form of a series, you can't find the IOC. You need to have that closed form. You need to have that summation notation. You have to have that compact form. So if we were going to find the IOC here, we would need to be able to find closed form. I won't ask you to do this on a test because it can be so stressful to try to find it. Let's see if we can do it here, though. So that part, I think, is pretty obvious right out of the gate. That start at 0. That's going to be the exponent on the x minus 1s. That's also going to match the factorial in the denominator. The only thing we have to deal with are those coefficients. And can you see what those coefficients are? Do you see what those are?
One, two, three, four.
So this one is a 2. This one is a 6. So the pattern that we're trying to establish is we have a 1, a 2, a 6, a 24. And we also have the switch. The switch we can do pretty easily. Let's do the switch in there too before we talk about those numerators. So the switch is -1. Is it going to be to the k or to the k plus 1? If we want this first term positive, if we plug in a 0, do we want to start at k or k plus 1? Up here. K. K will do it, right? K is 0, -1 to the 0 is positive. So that's the part I'm asking about right in there. So the pattern that we're trying to figure out is this, those guys. And those guys should look very familiar. 1 factorial,
Yeah, it's
2 factorial, 3 factorial, and 4 factorial. Right? 4 factorial is 4 times 3 times 2 times 1, which is 24. So does that line up with k, though?
No, it's k plus 1.
K plus 1 factorial. That's what this numerator is going to be, is k plus 1 factorial. And so you can see why putting this on test would be so stressful. Trying to find a pattern when there's a time pressure, that's like a hard thing. So I won't ask you to do this on a test, but when you're doing your homework, it's a super good mental exercise to try to do these things. And we know how this reduces. K plus 1 factorial over k factorial?
Just k plus 1.
Just k plus 1. So that's going to be, this is our power series then, AKA our Taylor series. And now we would have to find the IOC. You would do that with the ratio test. We don't want to do that right now. We have bigger fish to fry. But this would be good practice to make sure you can do it. And using the ratio test will make the most sense here. There is a power on the outside, but if you did use the root test, you'd have to take the kth root of k plus 1, which might get a little squirrely. Ratio test will work really quickly, though. All right. Let's take a look at another one. So we see sine. And we might say, ooh, let's use the sine power series that we know has all the odd powers from e to the x, except we throw in a switch. But then we see that the center is not 0, so all bets are off. You can't take a power series centered at 0 and modify it to turn it into a power series centered at some other number. We can't. That's unfortunately not something we can do. So as soon as we see that the center is not 0, start breaking it down, start taking derivatives, start building. Break out the pitchforks. Just get into the trenches, start taking derivatives. And we said 4 non-zero terms, so we want to at least go down to here, and we're hoping that none of those are 0. If they are, we have to keep going. So column 1, the function and its derivatives. Column 2, evaluate at pi over 4. And so what we see is that these coefficients are going to all be some sort of root 2 over 2. Positive or possibly negative. Notice that this series that we are going to create has negatives, but it's not alternating. Bless you. So this series will have negatives, but it's not going to be alternating. So this gives us a way to actually create series that are that have negatives but aren't alternating. So we are going to call our polynomial P, and so this will be, and by polynomial I mean infinite polynomial, I mean never-ending polynomial. And the center was pi over 4, so there is our tangent line. Tangent line, constant plus constant times x minus the center. That's tangent line. Now we're going to go to the best quadratic approximation, aka p sub 2. We have negative root 2 over 2. But then we have to multiply in the denominator by 2 factorial, or just 2 if you want. And that's going to be x minus pi divided by 4 to the 2. So that's the best quadratic approximation to the function, the best fitting parabola. And then we go to our last non-zero term that we're going to put in here. We have root 2 over 2. We have to multiply by 3 factorial, x minus pi fourths to the 3, but then plus dot, dot, dot. So p sub 4 plus dot, dot, dot. That is our Taylor series. Bless you.
Thank you.
Spring is sprung.
Yeah, apparently.
So that is our never-ending polynomial. It's our Taylor series. It's our power series that represents sine at pi over 4. And then if we wanted to create the closed form, here it's actually going to be, I think, even easier than the last one, because we have this constant of root 2 over 2 all the way through. And then we have a 1 over k factorial. And then we have an x minus pi over 4 to the k. K starts at 0. I think that's it. Do you agree?
Doesn't it need a switch?
And it needs a switch. Thank you. So we're almost there. We've got the magnitudes, but then we need a switch. Negative 1 to the k or k plus 1? K. Because this starts at 0, negative 1 to the 0 will give us a... Oh, no.
It's like every other two.
Oh, yeah. There's no... It's not alternating. What do we do? Can we do that? This problem said that we should be able to do it, but... Great point, though. So, there is some... I got to think about that, actually. There is some sort of switch-y thing. When we do the root or the ratio test, we do take absolute values. So the most important thing is this magnitude part. We could do the ratio test or the root test, not the root test because there's a factorial, but we could do the ratio test on here, even if we don't know how to represent those negatives, because we take absolute value when we do the ratio test. I've got to think about that during the break, if there's a way that we could do this plus, plus, minus, minus. I can't think of a pattern way to do that, though. So, but we could find the ratio test of the a sub k part, the absolute value of a sub k, and find the interval of convergence. Let me think about that part, though. Yeah, it's not just a switch. Let's think about it. All right. So, big difference here. Here, let's look at a Maclaurin series, so a Taylor series, but the center is at 0. As soon as we are trying to find a power series representation of a function and the center is 0, we should be thinking of those common power series. And the most common power series of them all, which you want to know, you want to have that one definitely memorized, e to the x, x to the k over k factorial, interval of convergence, all reals. As soon as we want to create one for something centered at the origin, let's grab one that is one of the known common power series. Because all we have to do is this. Replace x with?
e to the negative x.
So the x part is just being replaced with negative x. Yeah. And so this x right here in the power series is going to get replaced with a negative x. That is all we have to do. So the power series for e to the negative x, we just come into this power series, replace that x with negative x, and simplify that. So the simplification here is nothing more than popping the switch and isolating the x part of it. So we have that. We also have to replace the x in the interval of convergence with negative x. But when you multiply by -1, don't you end up with the same? And normally we wouldn't write it that way. We would normally, of course, flip it and write it this way. So there is our IOC, and that's our power series. So this replacement, this substitution or composition thing is super slick because you don't have to do anything. You just go to the IOC and modify the IOC. You don't have to test endpoints. You don't have to do a ratio test. All that stuff is shortcutting if you're doing a substitution. Okay, here's Cosh. Again, just note, I'll try to say as many times as possible, Cosh is exactly the even powers. Cosine and cosh are even functions. They take the even powers from the exponential. Cosh is exactly, we don't have to modify anything. Cosh is exactly the even powers. All right. And again, this says centered at 0, which makes us think, let's grab one of our common power series and see if we can modify it. So what are we going to do here with the x? We're going to replace the x in the power series that we know with 3x. So the power series for cosh of 3x, we replace the x with 3x all the way through. The power series is going to be that. And the IOC, we also have to replace that with 3x. So the one simplification that we like to do is to get the x's pulled away from that constant that's in front of it. So I think that, and it doesn't really matter, but I would write it, this is the way I would be inclined to write it. And it starts at 0. And if you divide everything of this IOC by 3, not much changes. So your IOC is still going to be all reals. So you can write it in, you can write it either way. Writing it in interval notation is nice simply because you can call it I. So, not too crazy. Not too crazy. Any questions on that substitution idea? Yeah.
You say you're going to tell us which ones to memorize?
Yes.
And we'll memorize the summation and the interval?
Yes, so I'll ask you to memorize e to the x for sure, so you should know the summation form. And the expanded form you should be able to create from the summation form. Or vice versa. If you have the expanded form, you should be able to get to that. But yeah, both. You'll want to know both. Because if we're doing an interval of convergence or anything, or if we're rewriting we are going to want to have it in that form to do our substitution or multiply by power of x. Yeah?
Can we have the 5 today?
E to the x for sure, geometric series for sure, binomial series for sure. And then I've got to figure out if it's going to be sine and inverse tangent or cosine and inverse tangent. The other one will be from, the other two will come from sine, cosine, inverse tangent. None of the log ones. Those ones are hard. Those ones are harder. But so it'll be, you know, sine, cosine, sinh, cosh, or what was the other one I just meant? Inverse tangent. Inverse tangent is probably a yes. Because we do so much with inverse tangent. It's a function that we encounter a lot in engineering classes and in differential equations classes. So, but definitely e to the x, definitely geometric series, and definitely the binomial series. And then probably arctangent, and then either sine or cosine. So yeah, look at those 6 up there, or the 12, and really just sort of look at the patterns, because they're way easier to memorize than sounds when you first look at them. The first 6, if you have the geometric series memorized, which you should, because we've been doing that geometric series for months, and then e to the x is the other slide. Okay, so now we come to this, and we're in the same boat. We want to find the power series for natural log of x, but the center is e. And once again, if the center is not the origin, you just start differentiating. You use our Taylor polynomial process, which we extend to a Taylor series. So we're going to start with our function, y equals natural log of x. And then y prime is going to be 1 over x, which I'll write as x to the negative 1. And then y double prime we'll write this way. And we want 4 non-zero terms. So we'd have that. None of those are 0 because our center is e. So that's great. So our second column is what it always is. We evaluate the function and its derivatives at e in this case. Y double prime of e is going to be minus 1 over e squared. Y triple prime will be 2 over e cubed. So then our polynomial, our never-ending polynomial, starts with that. So that part is the best linear approximation. Best quadratic approximation, we're going to have 1 over e squared, but then we have to stick in a 2 factorial and an x minus e to the 2. And then our next term is going to be positive 2 over e cubed multiplied by 3 factorial. And then x minus e cubed. And we want a Taylor series, so we make sure to put the plus dot dot dot. Now, we would need, if we're going to find the interval of convergence, we'd need to write the closed form of this, the summation form of this. There's no modification happening here. If we start with a known power series with a known interval of convergence, then we just have to fiddle with that interval of convergence. But here, when you start from scratch, and we're just building this power series, the only way to find the interval of convergence for this would be to find the summation notation form of this and then use the ratio test. Or possibly the root test, but this has factorials, so we would use the ratio test. But this one, bless you, is also kind of a little squirrely because it's not an alternating series. So we might have to shortcut, and I got to go think about this in my office for a minute. We might have to shortcut if we were going to do the ratio test and just say the absolute value of a sub k is equal to such and such. because we may not be able to get a pattern for the minuses with a, whatever, a -1 to a k type thing. Okay, let's take our 10-minute break, and I'm going to go meditate on that, because that is a great question. Daniel, that was amazing. Where was that?
One slide earlier.
How does the ratio?
We gotta go look this. We gotta go look that up.
Because we can.
Worksheets due tonight midnight.
Well, let's just pretend like we're evaluating the versions for this, and let's just do it out here. So, if I were to do the ratio test for this, then I'm going to add 2 over 2 times the weighted SK versus x minus pi over 2k times
The number
k over k. Didn't have the k plus 1 factorial. This is k plus 1.
I swear they didn't do it.
Actually, k plus 1. And then I would multiply that by my inverse, which is going to be k factorial x minus pi over
We are lying. And usually I have to if I'm trying to do that, I'll have to
So what's going to happen here?
ride myself.
These are canceling. You
Like
get k plus 1
show I want to
on
watch or something
and then
like
here
dairy
we
food,
get
but
x
breaks or
minus
something,
pi
like if it's
on
easy enough, kind of like
Right.
keep it
Oh,
on
they
in
would
the
do
background.
on top.
Kind of quietly, and then
over
I'll miss it afterwards,
k
going back 10 minutes, every 10 minutes. But for some, it
Uh,
just feels like I have to try and trick myself into thinking, I'm not just waking up to do homework, I'm waking up to chill, and I'll just have to
And what's
do
going to
homework
happen
chilling.
Yeah.
is theoretically this is going to go to 0.
I actually feel a little better when you said not the logs,
Meaning
that's just less
the
shapes
answer is
kind of
just
to memorize.
Oh, yeah.
It's already
like
complicated in
this
that.
last.
I know.
Had we gotten an answer that was a whole
I'm
number,
at least
we
glad
would have
that
ended up
this
with an
whole
equation
chapter
where,
is
okay,
kind of
x minus pi
all
over
one theme.
4 over
Like
6.
some of the previous chapters have been a little bit of this.
X, I think,
But
is
you have to remember.
Who's on that team?
I think I forgot.
That's a really good point, actually.
I'm saying it's magic. I generally don't know how that.
All I remember is
With
that,
the 10 and 11.
because I already forgot. because I did,
It's
I
not-
wrote it down to me. I remember is that eventually when you take this limit, you'll get to a point where you can almost solve for x.
Yeah, yeah.
And then,
I feel like too,
But
there's a
in
lot
this
of
case,
things where it's
since we're just
Yeah,
going
it
to
was
zero,
kind of like this in Calc 1 too, where you learn something and then they just kind of cut you off because they're
I
like,
think.
you're gonna need to know this in a later math class.
Which is the
For
point.
now, Don't
Which
worry.
should be true.
Like, know the
Because the whole
basics
point
and
of these power
don't think
series
about
is
it.
that
Don't worry
no
about
matter
what
what
goes on under the
they are
hood.
equal to
We just
the
know that this
actual
is true
function
because
for
some
all
really smart guys
values
figured it out.
x.
Yeah.
So it
And
should,
you just have to,
if you did it right,
go
go to
along with
0.
it, like,
It was
oh
really
yeah,
neat and all
just
that.
because it works. Like, but why does it work?
But I don't think that's not right.
I don't know.
So let me look at this. Which are really messy and
They were
shitty,
zero
so I don't
defense,
know.
of course.
Every
they
day.
were
When we did it,
170 is great.
That's a good idea, yeah. I'm
Stuff
hoping,
like this.
I'm glad that I have my
You see?
physics exam this week.
Mhm.
Pretty sure that I don't have anything else really majorly important going
Oh,
on next
okay.
week.
So what happened here was that when we did
Yeah.
Oh,
Yeah.
one of these, I ended up with this limit here, where you have the limit as k approaches infinity of k plus 1 times x minus 10 equals infinity.
I've heard from my boyfriend.
So infinity times x minus 10.
I did the same thing.
Alright.
But if we want that to go to 0 for coordinates, we would have to make this 0, which is why x. I don't know.
Just purely looking at numbers, our class started with, I think, around 22
Yeah.
and literally half the class was
Here?
half.
Yeah.
We're down to 11.
Well, the whole goal we want it to equal 0.
That's crazy.
Well,
Like, actually.
It's because her grade scale is esoteric.
Only way to make this 0 is if x equals 2.
Yeah,
Because that means our
used
radius
to like
convergence.
essays in like
I feel like if Jim
high school,
wasn't-
how they have like the rubric. It's like
Oh,
I think
yeah.
partly proficient. incomplete example. Everything is like that. So you can get like a proficient on one section of your exam, but it doesn't. So it's impossible to know hey, should I do retakes for this or something else because you don't know what your total score is.
There has to be maps, and there has to be.
She also, to my knowledge, still being graded in your labs from the entire year.
But that's
Like-
different than that. It could have been.
Like a major chunk of our grade.
So I'm going to do
That's the best job, because if like, they have like a grade and it's low,
I'm gonna ask
and they don't know what they got on the lab, so like, I don't wanna
Let me see.
fail.
I really hate talking to ChatGPT.
Oh, no, they
Yeah,
lost.
Sometimes you
I think that's kind of solidified that I don't want to take
I'm gonna ask ChatGPT.
Isn't that?
No, that's what she.
Too far through to pull that out.
So that's fine.
Well, I'm actually very
So then I'll
curious.
just have, like grade paper class, you made it like this, be like, the big words.
The Taylor series.
Yeah.
I think I should do, that'd be awesome.
This is going
I like game
to
seven.
cost probably 2 villages of water. Do you think
That would be insane. I think it's seven.
Australia is not gonna be an island anymore.
Answer right the first one, they're on.
Drain Stanley Lake? So
About
this weekend.
the NFL, the 72 game like the NBA, bro.
That was the last.
Could you imagine, bro?
It's a little more
I feel like,
exciting
I
though,
think
than
they're
rosters that you have to
had
have.
a little.
Sure. Like it's one of those,
No, it's me
it's just
actually.
like some sport, but knowing that it's gonna get better as time goes on. It's not too bad. Cause like my,
I feel like I'll probably like crush Mark. Oh, no, I feel
when
like
my
I would
boss is
crush
done,
Mark.
I'm looking at
With the name
warnings and
online.
everything. This is like right after we get our
Raleigh, Ohio.
so it's not gonna be
That's
anything crazy, and then when we get back.
But don't worry, it'll all come back.
That's gonna be the bro.
Oh, yeah?
I've already done
That'd be like the Olympics, they play for like
So
the
is it
entire
a
year,
promotion
and they think
or
they're
just
just
like more responsibility?
I love either really, because I don't think he's gonna make it through.
What?
Especially like while I'm in school.
Yeah.
But if I need to run a show, it's less concerning if we're in inspections of it.
But
Okay.
no, look at what it's
More
doing.
like
It's adding two series together.
I can't figure out how to.
Because
Like, I started trying to send it to myself. but-
So it's saying that if you
Not
find
really, I'm
anyone.
just hanging out with that girl.
So you're
Then I'm doing
gonna send it to my computer
Just
through like
hanging
email.
out.
It doesn't send us an email.
But does that work?
Yeah,
That's
that'll be fun.
So if we were to plug in 0, we should get
he's playing in West Point.
So if you plug in 0,
And then one is something
you're gonna get 1.
That's
One
actually
times,
I don't know why
this
it's.
is gonna go to 0. No, this is gonna
Because
go
now
to
that you're like taking like pictures with your laptop.
That's too much Mello just, you know.
Oh, we have to do like those.
Those ones
quizzes
where he was like, I
for,
can't
the
read
next exam.
it. I'll just assume the best.
Sure.
I know, I feel like I always kind of forget about it. I never read until the last one.
There should be,
It's just 1.
there should be two, right?
There should be 2, like 10 and
Or,
11.
the Nets. You play for a couple of grades, really
So we
good.
get 1
You play with
plus.
So I was like, is it
Yeah.
Blues? But there's two Blues or whatever.
That's so weird. Why? Why? That makes no sense.
I genuinely thought that Nets would be one of the greatest teams of all time. I think we had Prime KD, Prime Curry, and
Does that have peach in it or something?
Lemon. It's supposed to be a generational team.
Okay.
And I just remember
It's like as close as you could get
But I remember they rolled
But
him
it's
out
good.
because they wanted to get a higher lottery pick.
You can get way closer to the
You can, I know, you can just, what's stopping you? Or you can just eat it.
He said he was going to
Yeah, absolutely.
but the team.
Really get pretty close.
immediate dehydration from
I'll take it.
I'm so confused, I'm like, why is
I got it.
sucking all the water out of my body.
You're causing pain to me too, bro.
We're good.
He's like, salad burger.
I had a patient come into the clinic, and he thought that he saw something on the internet and thought he needed more copper in his diet. So he started putting pennies in his drinking water. And he was drinking penny water, and then he got zinc poisoning. But it's just like, what?
The last two, I'm just like, yeah, it's.
First of all, he has no idea where that penny's been.
Because I
Like,
see him.
that penny has been all around the country.
Do you guys know the greatest integer function? Also known as the floor function in college algebra? That's how they make this switchy thing with a floor function. They notate it. Did I forget to hit the, did I forget to pause it? The floor function, they're going to do this kind of thing. The notation is k over 2 like that. And that thing will do negative, negative, positive, positive, negative, negative, positive. That'll create a pattern of double, double. So when this is 0 over 2 equals 0, and this of 0 is 0. The floor of 0 is 0. It's the greatest integer less than or equal to the value on the inside. So if you do a 1 over 2, the floor of 1 over 2, the floor of 1/2 is the greatest integer less than or equal to that. That's 0. The floor of 2 over 2, that's really the floor of 1. The greatest integer less than or equal to 1 is 1. And then the greatest integer, if you do 3 over 2, the greatest integer less than or equal to that is 1. And so you're going to get this pattern of 0, 0, 1, 1, 2, 2, and then you're going to have, 2 odds, 2 evens, 2 odds, 2 evens, 2 odds, 2 evens. Clever. Clever, clever, clever.
So it's to the k over 2 powers?
So it would be -1 raised to the floor function of k over 2. Super intro. Okay. Thank you for that. It's the first time I've ever had to dig into that. That's cool. Weird.
We have to give all the water back.
Weird scenes inside the gold mine. Okay. So, another Taylor series here. I just want to make sure that this thing is still moving and grooving. No, it's going. It's going. Okay, so one more Taylor series. We've got this function. Do you all remember how to differentiate this function?
It's itself times the natural log of the base.
100%. So if you have an exponential that's not a natural exponential, it's not an e, you have to modify it with the natural log of the base. And so we are, in fact, going to end up with powers of this natural log of 10. And we want 4 non-zero terms. None of these will be 0, so we really just need to go to p sub 3. Any questions on those derivatives? You see how that constant is just being modified each step of the way?
Oh, because ln takes this constant.
You see it? Yeah, because natural log of 10 is a constant. So the derivative here is the 10 to the x natural log of 10, but then you have to re-log the base, which then gives you a log 10 quantity squared. And now we plug in our center. Our center here is 2, so this will be 100. Y prime of 2 will be 100, natural log of 10. Y double prime of 2 will be 100, natural log of 10. Let's use their clever shorthand notation just for grins. Natural log squared of 10. Remember that that means natural log of 10 quantity squared. So those are our coefficients, or our constants, that we will use to build the coefficients. So our polynomial then, our polynomial will be 100 plus 100 natural log of 10 multiplied by x minus 2. So that'll be the tangent line. Constant plus constant times x minus the center. And then we're going to go to the next constant, 100 natural log squared of 10, but we have to divide by 2 factorial, and that will be x minus 2 quantity squared. So you see the pattern. Do we have any minuses in here? No. And then plus dot, dot, dot. No minuses. This one will be pretty easy to write the summation notation. We wouldn't have to deal with the switchy thing since everything is positive. And the pattern here is super obvious, I think, because these numbers all match. So we could come up with the summation notation pretty easily if we wanted to find the IOC. Okay. So anything nagging regarding Taylor series? So Taylor series, bunch of derivatives, build the Taylor series, put the plus dot, dot, dot. Anything nagging on it? So let's get into the next topic, which is super interesting. Super interesting. Binomial coefficients. Have we talked at all about binomial coefficients in this class? No. Have you talked at all about binomial coefficients in any other class? Stats? Anyone take stats? No one in here is taking stats.
Forever ago. Yeah.
Forever ago. Do you remember binomial coefficients?
No.
Okay. So let's talk about these binomial coefficients. So this notation is not a fraction. The way we pronounce this is P choose K. And the way it originates is from basic probability theory. And so the idea is, let's suppose you have 52 cards and you want to pick 5 at random. That would be 52 choose 5. So this notation, 52 choose 5, is going to tell you how many ways you could pick 5 cards from 52 cards. So the wording P choose K comes from a very practical application. It's going to get weird though for us because we're going to turn these things into negative numbers and non-integers, and so when you think of it in that context, that's a good way to think about it, 52 choose 5, but then we're going to generalize that to something much uglier. But let's first focus on the non-ugly part. So the definition of P choose K, you take the upper number, put it in the numerator, and you put a factorial. Lower number, you put it in the denominator and put a factorial, but then you modify the denominator with the difference, also with a factorial. Now, as far as we have ever seen, factorial can only be applied to a positive integer. We haven't seen anything like 3/2 factorial or pi factorial or anything weird like that. So when we think about factorial at this moment, we're thinking, integer multiplied by the next integer down, etc. All right, so that is the definition of P choose K. Let's go to Pascal's triangle. Anyone ever seen Pascal's triangle?
Yes.
Few of you, not everyone, but this used to be a common thing that would be taught in high school algebra. So Pascal's triangle is showing us the coefficients for this set of binomial expansions. So all these are binomials. Binomial is polynomial with 2 terms. The most basic binomial is x plus 1. So this row here, coefficient 1 and 1. Next row, when the power is 2, coefficients 1, 2, 1, and then the powers of x, of course, are going from 2 down to 0. Cubed, the powers are going from 3 down to 0, and the coefficients are 1, 3, 3, 1, etc. So these all match coefficients. How do you get the numbers in the Pascal's triangle? You just add the two numbers above. So if you add the two numbers above, that's how you get to the number below it. So we add these two, get a 5, those two get a 10, etc. So the numbers in the row match the coefficients of this binomial expansion. All right. Now, let's look at the binomial coefficients. They're called binomial coefficients for a reason. 5, choose 0. So we're focusing on this one right here. So 5, choose 0. Definition, 5 factorial over 0 factorial, and then 5 minus 0 factorial. By definition, 0 factorial is 1. Not intuitive, but we're going to say 0. That's by definition. It makes all the formulas really simple and no special cases. So if you define 0 factorial to be 1, there's your 1. That's the coefficient right there. This coefficient is going to be 5, choose 1. Plug in the 5, plug in the 1, take the difference, get the 5. All the way through. So let's get to right there. This one here, 5 factorial in the numerator, 3 factorial, and then the difference is 2. Do all the math, and you get to the 10. So these binomial coefficients do what they say. They find the coefficients for a binomial expansion. That's what those coefficients do. Now, we can shortcut this. That notation right there has a factorial in the numerator and 2 factorials in the denominator. We can shortcut this. If you look at this step all the way down, notice that this 3 factorial, the p minus k factorial, that piece always can cancel. All right, so those are canceling to get to this step. Those are canceling to get to this step. Well, this one's not that interesting. 1 factorial is canceling to get to this step. So you can always cancel this part right here. The p minus k factorial will always divide into the p factorial, and let's see what remains. So when we have a choose 2, we end up with 2 factors. We started with 5 and subtracted 1 until we got to 2 factors. 5 choose 3. We start at 5 and we subtract 1 until we have 3 factors. 5 choose 4. We look at the numerator and we start at 5 and we subtract 1 until we have 4 factors. So what that allows us to do is generalize p choose k. Instead of that definition, we can modify it to this definition. Key fact is that there's no factorial in that numerator. So all of a sudden, we have a way to evaluate the numerator without doing that repeated multiplication. No factorial there. That is going to be a dramatic generalization that leads us to that. So there's how you would write it out in mathematical notation. So we now can do a negative number for p. Because if the numerator is just repeated subtraction by 1, it doesn't matter. It doesn't have to be positive. We can do repeated subtraction by 1. And the pattern was, okay, let's do repeated subtraction by 1 in the numerator until we have 3 factors. And in the denominator, we're only going to have that lower number factorialed. -5, choose 4. Now, conceptually, we can't conceptualize that anymore as 52, choose 5 means how many ways you can pick 5 out of a deck of cards. Now we can't conceptualize it. -5, choose 4 doesn't make sense in that practical application context. But let's write this out. So this is going to mean start at -5, do repeated subtraction of 1 until we have 4 factors, and then we put a 4 factorial. So we now, this is what we do in math a lot, is we use some pattern from some practical source and then generalize it and create some extra mathematical structures. And so then we can simplify this. This will end up being positive, and 4 factorial, once we get rid of all the negatives, 4, 3, 2, this is all going to simplify to just 5. We can also stick a yeah.
Why is the example above that going down, but the one that you drew going up? It goes negative.
Oh, I didn't subtract very well, did I? Thank you. When you subtract 1 from -5, I was so puzzled. I was like, whoa, it's simplifying to just 5? That seems so unusual. Yeah, it's because I can't subtract by 1. -5 minus 1 is? -6. -6 minus 1? Thank you. Yes. Oh my gosh, I'm not telling anyone I did that. So again, it will be positive for sure. And this is going to be 4 times 3 times 2. So the 4 and the 2 are going to cancel with the 8. And then the 3 is going to go in there and give a 2. So we're going to end up with 5 times 2 times 7. So 70. Somebody double check that. If I can't subtract by 1 properly, I might not be able to multiply properly. So the next oddity, so the first oddity is that we took that upper number and turned it from positive to negative. The next oddity is that we can get even weirder and turn it into a fraction. If we just are doing repeated subtraction by 1, we can do it. So when we look here, we do 1/3, and we do a repeated subtraction by 1, but this one, we're going to stop at 2 factors. So this guy is only going to have 2 factors, so we only have to subtract 1 once. And then 2 factorial on the bottom, 2 factorial is 2, multiply these, and simplify. So let's see if we can do this one. Okay, at least it's a positive number. I'll have a better luck subtracting 1 from a positive number. So in the denominator, we're going to have 3 factorial. In the numerator, we have 2/5, and then we subtract 1, so minus 5 over 5. So we have minus 3 over 5. All right, that's our second factor. And then we want to subtract 1 again. We would like to end up with 3 factors in the top. So subtract 1 once more, and we have that. And then we'll simplify it. So the 3 factorial is a 3 times 2, and we're dividing, so those are going to cancel with the numerator. So this 2 and this 3 and that 3 factorial, those will all cancel. We'll end up with a positive because we have 2 negatives, and it looks like we're going to just have 8 divided by 125. So this is the generalized factorial. And we are going to use this to do some wild and crazy things. So the binomial series, you don't have to write that down. This is just the generalized form. Instead of doing the p choose k, all they're doing is changing the p choose k to that modified generalized definition of the binomial coefficients. So, all right, fair enough. Now, again, I mentioned this earlier. Finding the interval of convergence for a binomial series is very difficult. The series is going to converge. It's going to have a similar convergence as the geometric series between -1 and 1, but you may include or may not include endpoints depending on what your p-value is. So it's going to look very geometric series-like up here if p is less than or equal to -1. But then if it's between -1 and 0, you're going to add convergence at the right endpoint. And if p is positive, you add convergence at both endpoints. Again, that'll be given to you, though. You don't have to memorize that. That'll be given to you. All right, so this is how you should think of the binomial series. Think of it as the geometric series with this binomial thing as a coefficient. That's how you should think of it. When someone says binomial series, think, oh, it's just geometric, but the coefficients are binomial coefficients. So it's a modified geometric series, modified with these binomial coefficients. And that's how we should think of it. Now let's use it. All right. So we have a binomial. It's raised to the -3 power, and we want to find the series expansion for that and then approximate it using that. Now, I didn't put the instructions on this page. We should go to 4 non-zero terms. There wasn't something down here that I missed, right? I got to change. Oh, no, there is something down there. Oh, no, that's just old rubbish. That stuff should not. Let me edit quickly. So this, we already have that. So this stuff is old. Yeah, first time through new notes. Get rid of. So there are instructions. Yeah, it seemed weird that there was no instructions on the prior page. So this, we're going to do one example on this page. Was this the example on the next page?
Different.
It was different?
Yeah.
Okay, so those are our instructions. I'll retype those so that they're, it doesn't matter to you. Okay, so we want the first 4 non-zero terms as our approximation. So we would call that P sub 3. Well, it depends. If there's no zeros, it's P sub 3 for 4 non-zero terms. So first 4 non-zero terms centered at 0, and then we're going to approximate the quantity. So when we look at this, actually, let's leave that up there. So what we want to do is write our function as P choose 0. Let's just write it in general first, just so we get a little bit of habit going. So we're going to be doing this kind of thing. So it's going to look geometric, but with binomial coefficients. So we said 4 non-zero terms, and I'm going to put an approximation symbol there. So that's going to be our approximation. So we have to identify P. What is P equal to? So P stands for power. What's the power?
1/2.
1/2. So if we look at this 1 plus x and we rewrite it, P is the power on there. So the 1 plus x is the binomial. P is the power, P is 1/2. So this is going to be 1/2 choose 0 plus 1/2 choose 1 times x plus 1/2 choose 2 times x squared plus 1/2 choose 3 times x cubed. So that is our approximation. Now if you do a few of these, you're going to see very quickly that this is always going to turn into what? 1/2 choose 0.
0.
Not quite. Just not quite. The second one is going to turn into 1/2. The second one, when you do choose 1, it's always going to be whatever the p value is. So if we think about our definition of this, here we want to have one factor up there. This one, remember that 0 factorial is 1. And so this is going to end up being 1. It's going to be 1. We say it's 1 by definition. So this is always going to be 1. This is always going to be px, those two. All right. And then now we have to do math over here. So 1/2 choose 2. So we're going to start with a 1/2 in the numerator and do repeated subtraction by 1 until we get 2 factors. So this will end up being -1/8. So we have -1/4 in the numerator, divided by 2, we get -1/8. So that will be this coefficient, negative 1/8 x squared. And then we get to the next one, 1/2 choose 3. So once again, we start the numerator at 1/2. We do repeated subtraction by 1. And repeated subtraction by 1 is going to give us a numerator that looks like that. So we want to do repeated subtraction until we have 3 factors. This one's going to be positive. Let's see. So there's going to be, let's just write it out, just make sure everyone sees it. So let's just multiply out the numerator. So we're going to have 3 divided by 8 is the numerator. Denominator is going to be 6. And so we can treat this as 3 over 8 multiplied by 1 over 6. And that is going to reduce to 1/16. And that will be this coefficient. Did I simplify that right? No? Or yes? So 3 over 2 times 2 times 2 is 3/8. 3 factorial 6. I think that's right.
Yeah.
Yeah, I'm good with it. All right, so that is our approximation then. That is our binomial approximation for non-zero terms. And our goal is to approximate root of 1.06. So that's going to be approximately equal to, what are we choosing for the x? What is x? What's the value of x going to be?
0.6.
I just had a question.
Oh, yeah, sure.
Should the 16x cubed be
1/16. Thank you. Yes.
Sure, if I'll do something.
No, you are thinking clearly. More clearly than I am thinking. So what is the value of x?
0.06.
0.06. Right, 0.06. So x is what's getting added to 1. 0.06 is being added to 1. So this is going to be 1/2 multiplied by 0.06 minus 1/8 times 0.06 squared plus 1/16 multiplied by 0.06 cubed. So that is going to be our approximation amount. All right, so we'll type it into Desmos because Desmos can do that more quickly than I can do it. So first, let's get the 1.06 up here. So this is, a very good approximation, and then our binomial approximation is going to be. So I don't think we're going to be quite at the same. Whoops. Arrow 0.06 squared. Okay, so there is our approximation. There is, the Desmos gives us an approximation that's accurate out to that last place there. And how close are we? Desmos is accurate. All right, so how many decimal places is our binomial approximation good to? So, yeah, 1, 2, 3, 4, 5. That's pretty good for just going out 4 terms. So, pretty accurate. Okay, any part there that you have a question on? All right, so we did all that, All right, let's go to next slide. All right, you all try this one then. Are you ready to try one? Yeah, you're ready. You're ready. You're ready. You're ready. I believe.
They already did this one. This is it's still not very good. It's accurate to the 10th.
So we're going to agree on that generalized form up there. The p-value, the power is -3, so we have -3, choose 0, etc. Geometric series of modified coefficients. So this very first term, -3, choose 0, is always going to be 1. One way to conceptualize it, if you go back to the choosing cards from a deck of cards thing, if you did 52, choose 0, one way to conceptualize choosing 0 is that, okay, how many ways can I take nothing out of the deck? There's only one way, and that's to not pick anything. Okay, so you can think of it that way. If you try to do the math formula for any of them choose 0, it doesn't quite work out. So it's more of a definition that 0 factorial is 1 and p choose 0 is 1. So right away, the first two should be pretty instantaneous after you've done it a couple of times. You see that it's always going to be 1, and it's always going to be whatever p is for the second one. So did you all get 6 for your next coefficient? You get a 6? Did somebody get a 6?
Yeah.
All right, good. All right. At least someone. And then -3, choose 3. Make sure we subtract, go in the right direction. I think -10?
Yep.
Good. All right. We're on track. So then this is our approximation. This is our polynomial approximation for 1 plus x to the -3. So there's our approximation. Okay. What is x in this case? If we want to approximate this quantity, 1 divided by 1.1 cubed, that's approximately equal to what is x?
0.0.
0.1. So 3 times 0.1 plus 6 times 0.1 squared minus 10 times 0.1 cubed. Now we jump to our calculator. So we have 1 over 1.1 cubed. That's what we're approximating. We're going to approximate it with 1 minus 0.3 plus 6 times 0.01, so 0.06, minus 0.00. I lost track of the zeros. I think there's going to be 3. Do you guys agree with that number of zeros? Is that all what you came up with?
I just got 0.
Yeah, but there was 3. Yeah. Yeah, just got 0.75.
All right, so that one's accurate to 2 decimal places with our 4. Not quite as accurate as quickly as the last one, but not terrible. If you're a bot, you could do that so much faster. Your accuracy would be so good. All right, one more. All right, do one more, and then we'll move on to our last slide in 11.3. We'll do it together simultaneously. See if we come up with the same answer. Any questions on that one? Are you coming up with the same thing I came up with? Is that what your polynomial look like? So as soon as you do a few of these, hopefully this first part gets real fast, that part. And then these two, those, and on the test you'll be asked for 4 non-zero terms also. So that's the math in computing these guys. But pretty procedural, you know, it's not too complicated. Once you do a few of them, you start to see the pattern there. All right. Well, this one is asking us for the first 4 non-zero terms of the Maclaurin series. So that means centered at 0. So find the first 4 non-zero terms of the Maclaurin series for the following function. So this is a Maclaurin series just because it's centered at the origin. Okay. We now want to create a Maclaurin series for this. So that means we want it centered at the origin. So we already figured out this binomial series. We did that on a slide prior. Any idea what we're going to replace x with up here so that we can get a Maclaurin series? Any? Say again? So if we replace that x with x, so first off, do you agree that if we replaced x with x plus 3, we would end up with this? But if we replace x with x plus 3 on the right side, that's not a Maclaurin series, right? That center would be what?
3.
Negative 3. If we replace all the x's with x plus 3, so if we replace that x with x plus 3, we get that for sure. And if we replace all those with x plus 3, we don't have a Maclaurin series. We have a Taylor series centered at negative 3. So what we're going to do is modify this a little bit. If we do what Daniel suggested, we pull out the 2. Do you agree that those are equal? If you factor out the 4, it pops out as a 2. And then if there's no 4 here, you're doing the whole thing that we did back in, I don't know, long ago. Multiply that by 4 over 4. So the numerator 4 comes out. So what are we going to replace x with then? We're going to have 2 multiplied by, we'll replace x with x over 4, x fourths. Yep. So we're going to come up here. This is going to be 1. Notice that this we can't write in summation notation. This is a binomial series. And those binomial series, the only way to write them in summation notation is with that binomial coefficient notation, which is a pain. So a binomial series, we're only going to look at the expanded form. So we're going to replace all the x's we see with x divided by 4. So we're going to have x divided by 4 in the numerator here, divided by 2, minus x divided by 4 quantity squared divided by 8 plus x divided by 4 quantity cubed over 16 minus etc. So we have that. So we did a substitution, aka a composition. We don't need to simplify this if we don't want to. You can see the pattern here pretty nicely. It's not too bad to simplify this particular one because we don't go out too far. So it depends on what the question says. If I want you to simplify, I will say simplify. If I don't say simplify, you don't have to. If it says simplify, then you would do one more step here. If the instructions said to simplify, here we could simplify pretty easily, but you don't have to unless it's asked. So here we're going to divide by 16, and then 8 multiplied by 16 is 128. Somebody check that. And then we're going to have 4 times 4 is 16 times 4 is 64 times 16, whatever that's going to be. So if it did say simplify, you could do that. But if it doesn't, don't bother. Okay. One more thing we have to do, though. We substituted into the power series, so we also have to substitute into the interval of convergence, right? So the interval of convergence started at -1, less than or equal to, less than or equal to 1. Up here it's with x, but we replaced x with x divided by 4. So then we have to simplify this new interval. And our interval of convergence will be -4 to 4, including the endpoints. And we don't have to test them because we're substituting. Anytime we substitute, don't have to test. Okay. Now how about this one? Do we have to do any finagling here like we did with the one above where we had to factor out the 4? Or can we just replace x with -4x?
I think we can just replace it.
Yeah, we can just replace it. So replace all the x's with -4x. That's going to be 8. That's going to end up being a negative. So all the odd ones, the negative is going to flip the sign. So it's going to end up being with a bunch of negatives. Again, you don't have to simplify this. If it says to, you will, but if they don't, it's up to you. Oh, 4 times 4, 6 times 6. All right, so we got that. And then what else do we have to do? Interval of convergence. So the interval of convergence was -1 to 1 with an x, but now we replaced with -4x. So that is our inequality that's going to lead us to our new interval of convergence. So we multiply both sides all through by -1/4, switching the inequality symbol when we multiply by -1/4. So x is going to be in between those two numbers. Our new interval of convergence will be -1/4 over to 1/4. And we're going to include both endpoints. Any part of that causing you confusion? So the subtle one is this top one. That's a little more complicated. So we just have to remember that a Maclaurin series means centered at 0. And so we can't do a direct substitution up there. But we were clever and able to do it anyway. So, final section. Final section. This section is really not super complicated. The idea with this section is that we want to underscore that if you have a function, you can always replace it with its power series and do the math. So if you're taking a limit or a derivative or whatever, an integral, if you want or you need to, you can always replace the function with its power series and do the math. So this is a super common limit that you look at in Calc 1. You know, it's indeterminate form. You could use L'Hopital's rule and get to it. Or, oh yeah, here's doing it with L'Hopital's rule. We can also do it with a power series. So we know the power series for sine is the odd powers of e to the x with a switch. So there's the power series for sine. And then we can cancel this denominator with all these x's in the numerator. Like it's going to modify all of those and create this polynomial. 1x cancels with each of those numerators. This is what we're left with. And if the limit is as x goes to 0, all these terms are going to 0 except for the first term. So our limit is 1. And we get the same value. Right? We get the same limit. So you can take and replace a function with its power series. So let's go to here. So we've got this limit expression we want to evaluate as x goes to 0. It's indeterminate, 0 over 0. You could use L'Hopital's rule. But instead, now that we have this awesome tool at our disposal, we are going to use power series. So we're going to say the limit as x goes to 0. We're going to replace inverse tangent with its power series. And what I might do, just so it doesn't get too messy, I might put this negative x in the front so that the dot, dot, dot aren't getting in the way. So it's negative x plus inverse tangent. Well, inverse tangent looks just like sine, except there's no factorials. So there is the numerator. Denominator is x cubed. These two x's out in front cancel, right? We have a negative x plus x. Those cancel. So we have limit as x goes to 0. Now we cancel the x cubed term by term. We're going to have a negative 1/3. And then x squared divided by 5. And then x to the 4 divided by 7. Plus, etc. And what's that limit as x goes to 0? What will that limit be?
Negative 1 over 3.
Negative 1 over 3. Right, because all those other x's just go to 0. So the whole tail is 0. The only term that's non-zero is that first term. You could use L'Hopital's rule. L'Hopital's rule here would work fine. It's going to be a little bit messy because the derivative of arctan is 1 over 1 plus x squared. But all right, here's another common one you look at, the bow tie function in Calc 1. We've got that. In Calc 1, you look at the limit as x goes to 0, and you see that that limit is 0. This would be an indeterminate form. So what about at infinity? If we go to infinity, looks like the limit's going to be 1 if we just look at the graph. Let's see if it pans out, and if it is 1. So the limit of that as x goes to infinity. So we have x multiplied by sine of 1 over x. So we're taking the power series for sine of x, taking all the x's out and putting in 1 over x's. So this is going to be, replace that x with 1 over x. Now we're going to replace this x with 1 over x. So we're going to get that, 3 factorial x cubed in the bottom. Go to the next term, replace that x with 1 over x. So we're going to have 5 factorial times x to the 5th in the denominator, etc. So we've got that. Now we distribute this x that's out in front. X multiplied by 1 over x is 1. Then we just sort of go through, and we're going to be canceling a single x from each of these denominators. So we're going to end up with that expression. And we're taking a limit as x goes to infinity. So what's true about all those fractions? They're all going to 0. Yeah, these are all going to 0 because the denominators are getting large and the numerator is constant. So everything will be 0 except term 1, and our limit is, in fact, 1. So do you have to do that when you're finding limits? Of course not. You don't have to, but it's kind of a cooler way than using L'Hopital's rule. Use a power series. Take the scenic route. One more limit here. Another limit. Might be able to finish 2 limits. These go pretty fast. So the concept is the same. We're dealing with a power series. We have a power series expansion for natural log of x. This is centered at 1. So notice the interval of convergence is centered at 1. The numerator is x minus 1. The denominator, natural log of x, we're going to replace with its power series. We are taking the scenic route. We are not using L'Hopital's rule. That's going to be a minus next. And we can just stop there. I think that's enough. So then we're going to have a cancellation of x minus 1 all the way through. So we're going to end up with a 1 in the numerator. And in the denominator, we'll get a 1 right there. And then minus, we're going to have x minus 1 divided by 2. And then here we have one of them canceling. So we're going to have an x minus 1 squared divided by 3, etc. And this limit is as x is going to 1. So what is this limit going to be?
1.
So when we look down in that denominator, as x gets closer to 1, all the x minus 1s are going to 0. So all these terms down here are going to 0. So that tells us that our overall limit is 1 divided by 1, which is 1. Got a lot of limits that are equal to 1. All right, one more. You guys try this one. So we have another indeterminate form up there. 0 times infinity is an indeterminate form. You can't use L'Hopital's as it stands. You'd have to do some finagling, but you could. But we can use power series, so see if you can do it with power series. Most important power series, have that one memorized. X to the k over k factorial. Anytime you ever see e to the x, think of it as x to the k over k factorial. Ah. All right, so you should end up with another limit of 1. All these are going to go to 0. And we're going to have a limit of 1. Maybe I should create an example that doesn't have a limit of 1. So what we do here, we have our x multiplier in front, and then e to the negative x. What I'm going to do again is just pop this negative 1 to the front, commutative law of addition, just so that it's not after the dots, just to keep it a little cleaner. So it's negative 1 plus e to the 1 over x. E to the 1 over x is going to be 1 plus 1 over x. All these x's get replaced with 1 over x, which puts the powers of x in the bottom. And then we distribute this x, comes across, and it cancels with that x, and it cancels with a single x from all the terms. All those terms are going to go to 0, so our limit will be 1. All right, let's stop. Let's pause. Let's pause. Let's pause. Take a pause. Take a break. Well, have a good weekend.
I'm sure they probably
Hopefully it doesn't get too weird out there. Is it really going to snow?